Picture this. Everything you see, everything you can point to, every star, every galaxy, every tiny atom that makes you, well, all of that adds up to less than 5% of what's actually out there in the universe. Wild, right? Then there's another chunk, about 25 to 27%, made of something just as invisible, something we call dark matter. So, if you're doing the math, that leaves a whopping, almost unbelievable 70% of the entire cosmos made of something else, something we've named dark energy. We can't see it, can't touch it. Our current gadgets can't directly detect it. And yet, it's the main thing shaping the past, present, and future of our universe. So, what is this invisible, all-powerful cosmic mystery? That's what we're exploring today. For a good chunk of the 20th century, scientists who study the universe, cosmologists, had a pretty neat picture of how things should work. Thanks to Einstein's theory of general relativity, we knew that gravity was the big boss on large scales, shaping the cosmos. And we knew the universe was expanding, a huge discovery by Edwin Hubble back in the 1920s. So, the logical next thought, given what we knew about gravity, was that this expansion had to be slowing down. Think about it. You throw a ball up, and gravity pulls it back, or at least slows it down. In the same way, all the stuff in the universe, all those galaxies, stars, and that mysterious dark matter should be tugging on everything else, hitting the brakes on that cosmic expansion. The big question wasn't if it was slowing, but by how much? Was there enough stuff out there to eventually stop the expansion and maybe even pull everything back together in a big crunch? Scientists were really trying to measure this slowdown. The trick was to look at things incredibly far away. Since light takes time to travel, looking far into space is like looking back in time. If they could just accurately measure the distances and speeds of really distant objects, they could map out how the universe has been expanding. The big breakthrough came in the late 1990s from two separate teams of astronomers. They were using a special kind of exploding star called a Type Ia supernova as their cosmic measuring tapes. These supernovae are insanely bright, briefly outshining whole galaxies, which means we can spot them from billions of light-years away. Even better, they have a known, consistent peak brightness which makes them fantastic standard candles. If you know how bright something truly is and you see how dim it looks, you can figure out how far away it is. So these teams painstakingly hunted for and studied dozens of these faraway supernovae. They were expecting to find that these distant explosions were brighter than they should be if the expansion was constant. That would mean the universe was expanding faster in the past and had been slowing down since, but they found the complete opposite. The distant supernovae were dimmer than expected. A lot dimmer. This wasn't some tiny error, it was a consistent, head-scratching observation. The only way these supernovae could be so dim was if they were much farther away than their redshift suggested in a universe that was slowing down. The implication was enormous, a real shocker for cosmology. The universe's expansion wasn't slowing down at all, it was speeding up, it was accelerating. Imagine throwing that ball up, and instead of it slowing and falling, it suddenly shoots upwards, faster and faster, pushed by some invisible force. That's how stunned the scientific community was. It was like the universe threw a surprise party, and the guest of honor was this totally unknown energy with some kind of anti-gravity power. This discovery, that the universe's expansion is accelerating, was so huge, it won the leaders of those two teams the Nobel Prize in Physics in 2011. And that mysterious thing responsible for this cosmic speed-up? That's what we now call dark energy. Okay, so the Type Ia supernovae data was pretty convincing, but in science, if you make a huge claim, you need huge evidence. A discovery that flips decades of thinking on its head needs more than one piece of proof, no matter how good it is. Luckily, other cosmic clues started pointing in the same direction, building a stronger case for this weird accelerating expansion, and therefore for dark energy. Let's talk a bit more about why these Type Ia supernovae are such trusty cosmic rulers. These explosions happen in systems with two stars, where one is a white dwarf. That's the superdense core left over when a sun-like star dies. This white dwarf sucks material off its partner star. When the white dwarf gets heavy enough, hitting a point called the Chandrasekhar limit, about 1.4 times the mass of our sun, it can't hold itself up against gravity anymore. Boom! Runaway nuclear fusion ignites and it explodes as a Type Ia supernova. Because they all blow up at roughly the same mass, how bright they truly are is incredibly consistent. By comparing that known brightness to how bright they look from Earth, astronomers can figure out their distance very precisely. The 1998 observations showed these distant supernovae were dimmer and so farther away than they ought to be if the universe's expansion was slowing. This meant the expansion rate has actually increased over time, but the supernovae weren't the only evidence for long. Another key piece came from the cosmic microwave background, or CMB. The CMB is like the afterglow of the Big Bang, a faint radiation filling all of space. Think of it as a baby picture of the universe when it was only about 380,000 years old. Tiny differences in the temperature of the CMB show us where the seeds of future structures like galaxies and galaxy clusters were. Satellites like WMAP and later Planck have mapped these temperature spots with amazing detail. The patterns they found, especially their size and how they're spread out, are super sensitive to the overall shape of the universe and what it's made of, including dark energy. When cosmologists crunched the numbers from the CMB, they found the data perfectly matched a universe that was not only flat, meaning its geometry is what you learned in school on large scales, but also made up of about 70% dark energy. Without dark energy in their models, the CMB data just didn't fit. It was strong, independent proof. Then you've got baryon acoustic oscillations, or BO. In the super-early universe, before atoms even formed, the cosmos was a hot, dense soup of particles and radiation. Sound waves, or pressure waves, rippled through this primordial gunk. These waves, the BAOs, traveled for a few 100,000 years until the universe cooled enough for atoms to form, and light went its own way from matter. At that moment, the waves basically froze in place, leaving a signature on how matter was spread out. This signature means galaxies are just a tiny bit more likely to be found at a specific separation from each other, the distance those sound waves traveled before they froze. This standard ruler can be measured by looking at how galaxies are distributed today. By measuring this preferred distance at different times in the universe's history, by looking at galaxies at different distances, and therefore different times, astronomers can trace how the universe has expanded. And guess what? The BAO data also points to an accelerating expansion, fitting right in with the supernovae and CMB findings. Finally, there's weak gravitational lensing. Einstein's general relativity tells us that mass bends space-time, so light from distant galaxies as it travels towards us can get bent if it passes by massive things like galaxy clusters. This bending effect, called gravitational lensing, can slightly distort the shapes of those faraway galaxies. By studying these tiny distortions across millions of galaxies, astronomers can map out where the mass, both the normal stuff and dark matter, is in the universe. These maps also tell us how structures have grown over cosmic time, and this growth rate is affected by how the universe has expanded. The observations from weak lensing studies? You guessed it. Also consistent with a universe dominated by dark energy that's causing it to speed up, so it's not just one thing, it's a whole bunch of evidence from completely different kinds of observations: exploding stars, the Big Bang's afterglow, how galaxies cluster together, and how gravity bends light. They all paint a remarkably consistent picture. The universe is expanding, and that expansion is getting faster, driven by something we've dubbed dark energy. This isn't just a small adjustment to our cosmic theories, it fundamentally changes how we understand what the universe is made of and where it's headed. Knowing that dark energy is out there and makes up roughly 68 to 72% of the universe is one thing. Figuring out what it actually is a whole other, much tougher ballgame. Right now, dark energy is more like a label for something we see happening than a thing we truly understand. Still, physicists and cosmologists have cooked up a few leading ideas. The simplest and most popular explanation, at least in the standard playbook of cosmology, called the lambda-CDM model, where lambda is dark energy and CDM is cold dark matter, is the cosmological constant. This idea actually goes all the way back to Albert Einstein. When Einstein first came up with his theory of general relativity, most people thought the universe was static, not expanding or contracting, but his equations naturally pointed to a dynamic universe. To make his theory match a static universe, Einstein added a fudge factor, a mathematical term he called the cosmological constant, represented by the Greek letter lambda. This term stood for a constant energy density that was just part of empty space itself, a kind of vacuum energy. It would create a repulsive force to balance out gravity and keep the universe still. Later, when Edwin Hubble discovered the universe was expanding, Einstein famously said the cosmological constant was his biggest blunder. It seemed like it wasn't needed, But jump ahead to 1998 and the discovery of the accelerating expansion, and suddenly Einstein's blunder looked incredibly smart. If this vacuum energy exists and has a small positive value, it would make space itself expand faster and faster. The nice thing about the cosmological constant is its simplicity. Its density is the same everywhere and at all times. As the universe expands, new space gets created, and this new space comes with its own fixed amount of vacuum energy, leading to a continuous outward push. There's a massive problem with this idea though, often called the cosmological constant problem or the vacuum catastrophe. When theoretical physicists try to calculate how much vacuum energy there should be based on quantum field theory, our best theory of particles and forces, they get a number that is mind-bogglingly, almost laughably, huge. It's about 10 to the power of 120 times larger than the value we actually see for dark energy. That's a 1 with 120 zeros after it. This is quite possibly the worst prediction in the history of physics. So this mysterious dark energy makes up most of the cosmos and is shoving galaxies apart faster and faster. Why should we, tiny humans on a small planet in a seemingly ordinary corner of the universe, care about this? Well, dark energy isn't just some abstract idea for scientists. It's fundamentally shaping the structure, evolution, and ultimate fate of everything. Think of the universe as a giant cosmic tug-of-war. On one side you have gravity, created by all the matter, both the normal stuff like stars and planets and dark matter. Gravity is attractive. It wants to pull things together, to form galaxies, clusters of galaxies, and all the cool structures we see. For the first several billion years after the Big Bang, gravity was winning on large scales. It diligently gathered matter into the cosmic web of filaments and voids that we see today. On the other side of this cosmic tug-of-war is dark energy. Dark energy acts like a kind of anti-gravity. It has negative pressure which, according to general relativity, makes space itself expand. For the first roughly 9 billion years of the universe's life, matter and its gravity were stronger, or at least kept dark energy from taking over. But as the universe expanded, the density of matter got diluted. Imagine a room full of people. As the room gets bigger, the people get more spread out. Dark energy, if it's like the cosmological constant, doesn't work that way. Its energy density stays constant. About 5 to 6 billion years ago, we hit a tipping point. The ever-thinning density of matter finally dropped below the constant density of dark energy. Dark energy became the main ingredient in the universe's energy budget, and its repulsive push started to overpower gravity's pull on the biggest cosmic scales. This is when the universe's expansion started to accelerate. This acceleration has huge consequences for how cosmic structures form. While dark energy doesn't stop gravity from making galaxies or clusters locally, it does make it harder for new super-large structures to form. Basically, dark energy is putting the brakes on the growth of the largest cosmic structures. But maybe the most mind-blowing thing about dark energy is what it means for the ultimate fate of the universe. What's going to happen trillions upon trillions of years from now? The answer really depends on what dark energy is, specifically, whether its density changes over time. If dark energy is indeed Einstein's cosmological constant, then the universe will keep expanding faster and faster. Despite everything we've figured out over the last couple of decades, the plain truth is that dark energy is still one of the biggest and most exciting mysteries in all of science. We've given a name to 70% of the universe, but we're still mostly clueless about what it fundamentally is. This isn't science failing, it's a sign of just how huge and complex the cosmos is, and it's an invitation to push our knowledge even further. The leading idea, the cosmological constant, fits what we observe pretty well, but it comes with that massive theoretical headache, the 120 orders of magnitude difference, the vacuum catastrophe. This problem alone hints that there's some deep piece of the physics puzzle missing, maybe pointing towards new symmetries or laws of nature we haven't found yet. To make headway, cosmologists are using more and more advanced experiments and surveys designed to measure how the universe has expanded and how structures have grown with mind-blowing precision. Several major projects are leading this charge. The Dark Energy Survey, DES, which recently finished its observations, has already given us some of the most precise measurements of dark energy by mapping hundreds of millions of galaxies and thousands of supernovae. Currently running is the Dark Energy Spectroscopic Instrument, DESI. Set up on the Mayall telescope in Arizona, DESI is making the largest 3D map of the universe ever by measuring the light signatures and therefore redshifts and distances of tens of millions of galaxies and quasars. Early results from DESI, which came out in April 2024, have started to suggest that dark energy might not be a simple cosmological constant. Looking further out, the European Space Agency's Euclid mission, launched in July 2023, will survey billions of galaxies to study both weak gravitational lensing and galaxy clustering. And then, there's the Vera C. Rubin Observatory in Chile with its Legacy Survey of Space and Time (LSST). These projects and others like them are humanity's best shot at uncovering dark energy's secrets. What if dark energy really is dynamic? What if it changes over time? The coming decade promises to be a golden age for cosmology, as these next-generation surveys deliver their loads of data. The quest to understand dark energy is a great example of how much we've learned, and how much more there is to find out. If you're as fascinated by these cosmic mysteries as we are, and want to keep up with the latest breakthroughs, make sure you subscribe to our channel and hit that notification bell so you don't miss our future adventures into the wonders of the universe. And we'd love to hear your thoughts. What do you think dark energy might be? Is it Einstein's constant, something more exotic, or a sign that our theories need a serious rethink? Let us know in the comments below. So there you have it. A staggering 70% of our universe is made of dark energy, a mysterious something that's making the cosmos expand faster and faster. We know it's there mostly because of how it affects things on a huge scale gravitationally, pushing things apart instead of pulling them together. From the dimming light of distant supernova, to the subtle patterns in the cosmic microwave background and the way galaxies are spread out, multiple lines of evidence all point to its existence. Yet, what it actually is remains one of the biggest unsolved puzzles in science. Is it the constant energy of empty space, as Einstein once thought? Or is it a dynamic field, changing over cosmic history, maybe even hinting at new physics beyond what we currently know? Current research with instruments like DESI, Euclid, and the upcoming Vera C. Rubin Observatory is pushing the limits, trying to uncover the secrets of this dominant yet invisible part of our universe. Understanding dark energy isn't just about filling in a blank in our cosmic shopping list. It's about grasping the fundamental forces that rule reality, the intricate dance of matter and energy that has shaped everything from the Big Bang to today, and that will decide the ultimate fate of the cosmos. It's a humbling reminder that even now, the universe still holds deep secrets, and our journey of discovery is nowhere near over. The fact that 70% of everything is a complete enigma isn't something to be down about, but a thrilling invitation to keep exploring, keep questioning, and keep marveling at just how vast and strange it all is.